Forget typical photosynthesis. What if there was a plant that literally feasts on toxic metals, cleaning up the most contaminated places on Earth? Intrigued? Keep watching. Ready to discover the surprising science of how these botanical superheroes are changing our world? Imagine a garden where the most vibrant blooms aren't nourished by fertile soil, but by heavy metals. It sounds like something out of a futuristic novel, doesn't it? Yet, tucked away in the incredible diversity of our planet's flora exist genuine botanical superheroes, hyperaccumulators. These aren't just plants that tolerate a little adversity, they are nature's extreme eaters. Picture a tiny mustard plant, Thlaspi caerulescens, contentedly drawing up concentrations of zinc hundreds, even thousands, of times higher than would kill most other vegetation. Or consider Alyssum bertolonii, which practically bathes in nickel. What's their secret? While most plants view these elements as deadly toxins, hyperaccumulators treat them like a vital nutrient buffet. They absorb them, concentrate them within their tissues, and astonishingly, thrive. How do they pull off this botanical magic trick? And what incredible purpose could such a specialized ability serve? The very compounds that would spell doom for nearly every other living thing become the building blocks of their remarkable existence, offering a tantalizing glimpse into a world where pollution isn't just clean, but eaten. We just scratched the surface, wondering how pollution could be eaten. But peel back another layer, and the true marvel unfolds, the metal-meal mechanism itself. Imagine, if you will, the roots of these botanical superheroes not just passively sipping water, but actively seeking out and latching onto specific metal ions in the soil. It's a highly sophisticated, almost sentient, selection process, where molecular gatekeepers decide what gets in. Once absorbed, these potentially toxic elements aren't left to wreak havoc. Instead, a microscopic high-speed transport system kicks into gear, swiftly ushering the metals up through the plant's vascular network. But here's the clincher: how do they avoid poisoning themselves? The magic lies in specialized cellular compartments, particularly the vacuoles. Think of them as tiny, impenetrable detox chambers within each plant cell. The metals are carefully shuttled into these vacuoles, effectively sequestered and locked away from the plant's sensitive biochemical machinery. Some plants even bind these metals to specific proteins, rendering them inert. It's an astonishing cellular ballet, a biochemical masterpiece that transforms what would be deadly for nearly every other living organism into a mere occupant of a cellular prison. And what extraordinary secrets might these precise pathways hold for our future? But which toxins, precisely, are we talking about? Imagine landscapes scarred by industrial neglect, not just any waste, but the insidious remnants of heavy metals. Think nickel, an often overlooked pollutant from mining and manufacturing, silently seeping into water sources and disrupting delicate aquatic ecosystems. Consider cadmium, a persistent byproduct of battery production and smelting, poisoning agricultural soils and threatening our food chains with its long, toxic half-life. And then there's lead, a notorious villain, a legacy of old paints and industrial emissions, infamous for its profound neurological damage to humans and wildlife alike. These aren't just abstract threats, they're very real dangers that these extraordinary plants confront head-on. Their unique biochemistry doesn't just passively absorb metal, it actively seeks out these specific culprits. Like microscopic wardens, the precise proteins we discussed don't just put these metals in a cellular prison, they specifically identify and neutralize nickel ions, encapsulate cadmium, and lock away lead, preventing their destructive reign. This targeted detoxification, this biochemical precision, isn't just fascinating, it's a beacon of hope. Could understanding these exact mechanisms truly be the key to reclaiming our most polluted lands, offering a clean slate for generations to come? What other toxic secrets might these green heroes unlock? Forget abstract scientific theory, the real magic of biochemical precision is unfolding right now, across the scarred landscapes of our world. Picture vast, desolate mining sites, their earth poisoned by heavy metals, barren and lifeless. Yet, here, the humble alpine pennycress roots itself, meticulously drawing zinc and cadmium from the soil, locking it away. Or consider abandoned industrial zones, where the very ground breathes toxins. Poplar trees become living filtration systems, their deep roots steadily detoxifying lead and mercury. Even our precious farmlands, subtly tainted by decades of runoff, are finding a gentle yet powerful cleanser in these green heroes. This isn't a distant dream, it's bioremediation in action. Witnessing fields once poisoned slowly bloom again, isn't it breathtaking to see the precise mechanisms we discussed offer such a tangible clean slate? Could understanding these exact mechanisms truly be the key to reclaiming our most polluted lands for generations to come? What other toxic secrets might these resilient plants be poised to unlock? Indeed, isn't it breathtaking to see the precise mechanisms we discussed offer such a tangible clean slate? But what if their genius extends even further, beyond simply neutralizing toxins? Imagine these same botanical heroes, not merely scrubbing our planet clean, but actively mining it. This isn't just remediation, it's phytomining, a revolutionary concept where plants don't just detoxify soil, they harvest valuable resources. Think of it, fields of hyperaccumulators, like a specialized mustard plant, not only pulling heavy metals like nickel, gold, or even rare earth elements out of contaminated soil, but concentrating them within their own tissues. They become living, growing, bioore. Once mature, these plants can be harvested, and their metal-rich biomass processed, often through a controlled incineration, to extract the concentrated elements. Instead of strip mining or harsh chemical processes, we're using nature's own gentle, sustainable methods to reclaim precious metals. What a paradigm shift! Could this green extraction method completely redefine our approach to resource acquisition, turning polluted lands into valuable, renewable mines? What other hidden treasures are these silent miners poised to unearth for a greener future? Yet, as we marvel at the vision of these botanical alchemists transforming polluted lands into valuable, renewable mines, a crucial question arises: what stands between this incredible potential and widespread reality? The truth is, even these silent miners face their own hurdles. Imagine trying to reclaim vast tracts of contaminated earth, plant by plant, when nature's pace can be painstakingly slow. Their meticulous work, though groundbreaking, often proceeds at nature's patient rhythm, a significant limitation being their inherently slow growth rates. This isn't merely an inconvenience, it translates to prolonged cleanup times and the need for expansive cultivation areas. But what if we could accelerate nature's clock? Scientists are diligently working to overcome these challenges, exploring genetic modifications to enhance metal uptake and growth, identifying faster-growing hyperaccumulator species, and optimizing cultivation techniques. Imagine a future where bioengineered plants, thriving at an accelerated pace, could rapidly detoxify industrial sites or urban soils. This isn't just about reclaiming precious metals, it's about reclaiming land, health, and hope. What ingenious adaptations await discovery, pushing us closer to truly sustainable resource management and unlocking even more of these hidden treasures for a greener future.